Hi everyone, my name is Kellen Villadu, and today I'll be presenting on Lab 3. The goal of this lab for part 1 is to analyze the motion of a star in space as it orbits a black hole in order to determine the mass of the black hole. For part 2, we have to analyze the motion of both the planet and a ship around a black hole in order to determine the initial velocity of the ship required to exit the orbit of the black hole. The models that we use for both part 1 and part 2 will be doing computational models. For one, we're using the star and black hole as a system, and then for the second one, we're doing the ship, the planet, and the black hole. Our results, the hypothetical results will be for part 1, that the black hole mass will be about 9 times 10 to the 33rd. For part 2, the lowest required initial velocity will be a vector negative 3.87 e7, 1.33 e6, and 0. The main physics ideas that we'll be covering is Newton's second law of momentum, where F net is going to be equal to dp dt. We'll use both the velocity and position update formulas. We'll use gravitational force as well as the gravitational constant. And something very important to this is the parallel and perpendicular components of forces and momentums. All right, so for part 1, the initial conditions will be using a C to generate a unique trajectory. And then we will have the gravitational constant, the mass of the star, and the delta of t, which will be 1 day as defined below. For the computational model, we have defined our momentums using the MV equation. We did use the F net equals dp dt equation. Parallel and perpendicular components of the forces and momentums, change of momentums. The last calculation, important calculation, would be the mass of the black hole, in which I used the average of the output values given by the code, and then you take the average by using a count, and that outputs as the final value. The average mass for the black hole is, as said before, 9 times 10 to the 33rd. F net is about 7.6 E28. The parallel and perpendicular components are also shown. For the discussion piece, what does it mean? The parallel and perpendicular components of the force and change of momentum are equivalent because F net is going to be equal to dp dt. So the parallel and perpendicular components will also be equivalent. So for part 2, we got the initial conditions we defined before, right? The mass of the black hole. And then we also have G, the mass of the planet, the mass of the ship, and delta T. The ship speed, we will show how I define those later, but I used testing and iteration to determine those values. In the computational model, the important things to look at are the net force on the planet, which is the total of the force of the black hole on the planet and the force of the ship on the planet, which you can see given by the extra r hat line used to define FBH on planet and F ship on planet. And then the next force value is the F net on ship, which is FBH on ship plus F planet on ship. And again, we use those extra r hat lines to help to define those values. And we just use the gravitational force equation to derive those values as well. For the velocity and position of the ship and the planet, we just use the velocity and position update equations. And after a bit of iteration and testing, in order to get to the closest value you can to get right around that planet, or right around the black hole, is negative 3.7 E7, 1.33 E6, and 0. So for the second part of the discussion, it's asking how would you orbit? Now, the easiest approach for me was to go for a circular orbit in which I could use the perpendicular value, which is the x value, just using the Earth exit velocity, which is negative in this case since we're moving away from the surface of the planet, square root of 2 gm divided by the difference in radius between the ship and the planet. And the way that I calculated that was using the potential energy of the Earth equal to the kinetic energy of the ship. And after simplifying, you get that equation. Now, it wasn't exactly correct the first time I input it. It actually crashed into the planet. So I just raised that constant from 2 to 3, and it ended up working. Not sure why that happened, but it's what I needed to do to make it work. And then for the parallel component, you just use the black hole circular orbit velocity, which is square root of the gravitational constant times the mass of the black hole divided by the radius of the ship minus the radius of the black hole. And to derive that, I used the force of gravity of the black hole set equal to the centripetal force of the ship. And that's G, mass of the ship, mass of the black hole over the difference in radius squared. And then you set that equal to the mass of the ship times the velocity of the ship squared over the radius of the ship. And once you simplify, you should get that equation above. And once you input those into the velocities for the x and y components, you should get a circular velocity to orbit it. Now for errors, right, I already talked about that 3 instead of 2 constant for the circular orbit equation. I think I'd attribute it to like an imperfect radius input. Maybe it's not exactly on the surface of the Earth.